Yeah.
So this is a very friendly note to all of my classmates in this class. Remember to back up your data, back up your data, back up your data. So this is a true story that on Thursday my laptop failed. I thought it's a system crash at first, but then it turned out to be a hard drive failure. I literally lost everything. 5 years cumulative of PDF materials, projects, photographs. I have a clean computer now, and I guess and then you guys all know that hard drive can fail, and back up your data, back up your data, back up your data, back up everything.
Okay, well, a good message. It does happen. It's a rare event, but it happens.
I lost everything, everything.
That is a bummer. Yeah, hard drive failure is real. Okay. Are there any questions? Okay, let's talk a little bit about, so what we were doing before, I talked about profiling and performance monitoring. So one of the ways that we did it in Python was to just run a Python script through this cProfile module, and then we can see where that Python script is actually spending its time. So let me, so we can keep the terms on the side. Request, let's write that down. Profiling. Just measuring a program to see where it's slow. That's it. And actually another bit of review that might be nice, actually. So here in my, I don't know why I put this in my PhD research, but some of the stuff that I did in with the database stuff. Oh yeah, I meant to say on that one thing, the comment about the data set being too big. So it's also a lot harder for me to make that big data set and to make these projects. It would have been a lot easier for me to give you kind of a standard out of the box just download from someplace really easy and have it be small and easy to analyze and clean. Way easier for me, but I did the big data set to give you the real hands-on experience. So I think that's it's something I'm excited about, and I'm glad you got to all see it anyways. So to make all this work, so what I'm showing you here is an R script that goes from the original source database where all this USA spending came from into a SQLite database. I did that because you guys asked to see SQL, and I'm going to give it to you in SQLite because that is definitely the easiest way for you to start playing around with SQL. Postgres is the database that it came in, and it's a big, powerful, industrial-grade database that you need to spend a lot of time setting up and tuning and configuring, and that's not the point when you're just trying to learn SQL a little bit. So what I did was go from the Postgres database into a SQLite database. The tables are too big to bring everything over all at once, so this same chunking streaming idea is what I use to get the data from one database to another. It doesn't have to be just a file. Anything that will give you rows or chunks at a time, you can do. So this is the R script with the packages. DBI is a database interface package for R. Python has one that's similar. Just like I have a file I'm reading from and writing to, we've been using standard in and standard out, or read from standard in and write to standard out. I can also just as well have it be a database that I'm going through. So, yeah, I got a lot of funny comments here, but this is not particularly. So what this function is doing is just taking chunks at a time, going through, reading 10,000 lines at a time, and writing them to the next database. And this is kind of the core of the actual loop, where I'm looping through the chunks. I'm just checking to see if everything has came through, and if it hasn't come through, while not database has completed, then fetch another chunk and append it to the table where I'm writing it. And then send me a message to standard output. So this takes like half a day or something to do. So rather than just run it and not have anything happen, I have it send me messages to standard output to tell me when to make sure it's actually running and doing something and not just hung. And then it tells me when it's all done. Then the core of the processing is just all these different table names. I take it from and to. So in the original database, they were called top tier agency, transaction normalized, recipient lookup. And in the new one, they're called agency, transaction, and recipient, which I probably should change the name transaction. Do you know why? That's the name of a table in my SQL database. Any idea why that is a bad name? Yeah, that's a keyword in the SQL language, transaction. So if I type just transaction, the database parser will recognize it as a keyword. So you have to backtick to escape it. But I'll probably change it to something else so you don't have to deal with that issue. So this is kind of a review of what we were doing with the streaming through. Any questions on this script? I know it's kind of just a brief high-level overview. I'll put a link to it if you want to check it out and look more a bit. The map. This is the thing that actually makes it all happen. Everything before that is just defining functions and setting up the connections. So map, my chunk copy table, it takes in two arguments, from and to, from two databases, and it it pulls from the from table and puts it in the to table in the other database. That's it. So I use map for that because map is like lapply, but it takes multiple arguments, in this case from and to. Right. Okay. All right, so now get into today's topic. I wanted to show you very briefly test-driven development. Has anyone used this before? Test-driven development? It's like unit testing, yeah. Have anyone heard of it? I knew people must have heard of this. Okay. All right. Heard of unit tests? Okay, it's definitely related to unit tests. So, yeah, this is one of the things that I didn't understand until I started doing open source software. So I'll tell you about the mistake I made. Maybe that would help clarify it. When I started with the open source software, I found a bug in some open source project, and I was like, oh, okay, maybe I should submit a patch and fix it. And so they're like, sure, yeah, submit a patch. So I submit a patch that fixes the bug. It's like some problem inside, whatever. I fix it, and they're like, no, that's not how you do it. So the way it works for test-driven development, you write a test that identifies the bug. So a test that fails with the current state of the software. Once you determine that that test is failing, then you write code to make the test pass. So the test is a specification for how you want your function or your software to behave. We've kind of did this before when I was writing the Python script, where I was doing the echo 1, 2, 3 and having it strip the first character off the last column. That was basically test-driven development. I was defining the spec of the test, what I wanted it to do, and then I wrote the software to make it happen. So I want to demonstrate how we would actually do it here. So people had some problems calculating KLD. There were a lot of questions on it to do this KLD calculation. So one way you can do it is with test-driven development. So you need a test for KLD. So I suggested to a couple people that so this is the actual formula, and I suggested to people that they just get their tests right out of this basic example in Wikipedia. So this has an example for how KLD should behave. So this is what the process looks like. So we write a function, KLD, function of P and Q, and put nothing in it for the moment being. We just write what it should do. So KL divergence between two discrete probability distributions. Okay, so this is what we want our KLD function to do. So we haven't written any code at all yet beyond the shell of the function, kind of an empty function. So now we write the test, and the test is exactly based on what we see in Wikipedia. So we've got this distribution P and Q sitting here. So we'll just use those. P1 equals 0.36, 0.48, 0.16. And Q1 equals rep 1/3, 3 times. R open. So here I'm setting up for my test. Wikipedia is going to define my test, assuming that Wikipedia is correct in how they calculated KLD. So the KLD of P and Q should be this number, and the KLD from Q to P should be this number. So this is I'm going to make a test out of this. So let's do it so I can still see that. So this is what I want to behave. I want KLD of P1 and Q1 to be close to 0.085 52996. So I need a function to check if these two numbers are close. Do they need to be exactly the same? Why not? Shouldn't they be exactly the same? Why should we not check if they're exactly the same?
64 is all right.
Yeah?
How the decimal approximation of the KLD will return a more exact value?
Yeah, so the one I'm writing in my code will be more exact than this. And we know this because this has only 6 significant digits. The one that I'm computing in R will have 16 significant digits for a double precision floating point number. So we need a function to check if they are close enough. So we can use all equal is one. So all equal, say the number 1.0 and 0.9999. Let's check. Okay, so it's saying that these are not all equal. They've got some relative difference, 1e negative 4. I want to check that they verify that they are. So I can specify the tolerance by which I'm checking. I can give an argument tolerance equals tol. And I'm going to keep this tolerance 1e negative 3. Try that. Run that. Okay, now it says true. So I can change the tolerance by which I'm checking if numbers are close enough. And 1 to the negative third, 0.001, that's close enough for this test. I just wanted to get it that close. Okay, so I need to make a test out of this, so writing our test. Any suggestions on how to write a test? Has any? Yeah?
So, P times log Q over Q, take the sum, drop it in A.
That's the code. That's the second step of test-driven development. Right. Yeah, so that's the code we actually need to write to make it pass the test. But yeah, go ahead.
Print.
Print?
Yes, print.
Yeah, okay. So we could print. So here's a way, print KLD, or we're checking all dot equal. Right, KLD in this with tolerance equals tol. Okay. Okay, so it says no function KLD. Of course, I haven't ran this yet. I'll run this and I'll have an empty function. Right now, KLD of anything will return. Do we know? Whatever an empty function returns. Null, probably. Null. Okay. So we can check if our test fails. So we get this printed warning or printed statement that says that these are not all equal. So we've written a failing test. So the idea behind a unit test is to automate the testing. With printing, we don't really automate it. Say we had written a whole big program using our KLD function. If the printing shows that our test is failing, then everything will still happen afterwards when maybe we just want it to stop at that point. So there's other unit testing packages. You can use other unit testing packages. Anyone use these? Test that. Test that. R unit, I think, is another one for unit testing. forget what's capitalized. But for quick and dirty, there's print, but slightly better than print, we can use stop. Stop if not, particularly. So instead of print, I'll put stop if not. So now, instead of just printing and saying that the results are not the same, we can use this stop if not. So stop is a function in R, and that just means raise an error wherever you are. Something has gone wrong, raise an error, bail out of there. Like save me from doing something bad. Stop if not is the same thing. It just checks if everything, all the arguments you pass to it are true. So right now it's raised an error and dropped me into my debugger, which is the behavior I want for a unit test. Any questions on that? So there's that. So we've done the two parts of test-driven development. We've written a failing test. That's what this is right now. We've got a failing test. Good for us. And also, like when you're doing this on a day-to-day basis, I often like to stop here. I write a failing test and then I go home for the day. And I like check in the code and it's all broken. A lot of people do this, but it's kind of nice because then when you get going the next morning or when you return back to it, you're like, oh, okay, that's where I was, that's what I was working on. And your brain is sometimes clicking through on things to do. So having broken tests is not a bad thing. It just means that's what I need to fix next. So it's kind of, I leave this to remind me where to go when I've forgotten everything that I was doing a day prior. So now let's fix our function. Let's give it an actual body and make it work. So people seem to have memorized this by heart. I know I haven't. Jared, you just said it. What was it? P times log P. Log P over Q? Okay. Sum temp. I'm going to do this. Let me see if this is. Okay. We'll start with this. So the suggestion was to also add na.rm equals true, right?
Yes.
Okay.
Wait, in that case, should we remove the RMs, the NAs, or should we like replace it with like some epsilon?
There's 0, so we can remove them. Yeah, because adding zeros to a sum won't change the sum. Yeah. Well, so log 0 is very large, but the p in front of it is also 0, so 0 times log 0 goes to 0 in the limit, and that's what we're kind of relying on, that mathematical property. So I guess I'll just write what it should be, so we can do this sum temp na.rm equals true. Okay? So, if I actually made this change right now, would it be test-driven development? So, will this fail if I don't have the na.rm equals true? So let's try it.
No.
Yeah.
You have to cause the failure with like the data, so you can never do KLDs one that has like a 0 or like a
So yeah, so we need to write a test that actually causes the failure. So let's make sure that this one actually passes. Okay? So I got my prompt back. It did not raise an error. That means that this test is now passing. And this is test-driven development. I wrote enough code to make it pass. So now we need to find a way to make it fail. And the thing that gives us trouble is when we have zeros in some entries, right? So we could say something like, instead of P1, we have P2, and put some zeros in here. So if we got 0, and then 1/2, and then 1/2, that's a valid, totally valid probability distribution, and we should get the right result for this. But do we know what the answer will be for this? I mean, I don't know off the top of my head what this 0.5 should be. We just want it to be not anything crazy like null or infinity or NA or anything weird. We do know that the KLD should be greater than 0 unless the distributions are the same. So we can use that property to write a test. So I'm just going to keep adding to the statements that I'm checking if they're true. So I just want to guarantee that 0 is less than KLD of my P2 and Q1. So this is enough of a test to kind of check that. Make sure I got those defined. Now I'm going to run this and I expect our second test to fail. Okay. And it did. It brought me into my debugger. 0, blah, blah, blah. PLD P2Q1 is not true. Now I have a failing test. Now I can continue to develop my code to address these tests that keep identifying the failures. And Jared already suggested the solution for that. So instead of sum, we do a sum with the na.rm equals true. So we keep modifying our code to pass the test. And it's a good idea to, if you're using version control, to stop and copy checkpoint, make a commit where you have every time you write a failing test and every time you pass, you have a passing test. Then you're continuing to modify your code, but you can always jump back to wherever you're making mistakes at. Or if you ever get off the wrong track. So now I've created our new function, defined it, ran it in the interpreter. Let's check if it passes the test. Run these tests again. And no failure. It all worked. Okay, everything came through, no failure. Any questions on this process? So, to reiterate, the order of writing things. First, I wrote the documentation for a function. Then I wrote the test, unit test, failing unit test, and then add just enough code to pass the unit test. And this is basically test-driven development. People like it in software development because it lets you kind of see this slow incremental process. And you contrast this with if in the very beginning, for example, for this last homework we did, if you're kind of looking at the whole pipeline, the thing that I drew across the entire board, and you're like, oh, I got to do this. So I write a function, process all the data, and that's super hard. These aren't decomposable into small little modular pieces. So the unit tests and test-driven development will do this for us. Make incremental improvements. All right, ready to move on to profiling? Okay. All right, so someone in this class gave me this code and asked how can we make it faster? And I think this is a really good use case for profiling. It's more useful for me to show your code than for me to be doing my code, because I write my code based on years of experience of doing this. So I'd rather work with your code. So this stuff is not important. It's just setting up the data for us to use. But this is so here's the actual code. Run that. So they have a KLD function, and it is exactly what we wrote for our KLD functions. So this is actually a great way to write it, I think. I mean, this is vectorized, it's short, line 21 here. I totally endorse this way of writing it. I just saved the sum as temp before I removed the NAs, that's all, or the vector. So the code does that, and then we got the actual Bootstrap part of things. So what the Bootstrap does is it creates a sample space by getting all of the numbers from the original distribution and samples from those with replacement. This is in contrast to the weighted sampling. So we talked about weighted sampling might be more efficient. By profiling this, we can see if this sampling is actually the bottleneck, if it's worth it to make it more efficient. This person wrote it in a way that made sense to them, and that's worth a lot. I mean, that's definitely the way you should do it first, is write it first in a way that you're pretty confident is correct and makes sense to you. And then go back and profile and see how you can improve things. So they make a sample, and then they take the proportions and calculate the KLD from the proportions. So that's the whole program. So we're going to use rprof to profile. And let me just grab the code where it was. Let's see. You don't need to watch me type all this out. Okay, my working directory is users Quark Scratch rprof demo, which is where that code was. Here I'm in that directory, so I see these are the files that are being analyzed and some outputs that are coming out. So I've removed rprof.out from here. So when R profiles, it does statistical sampling or uniform sampling. It just goes every 0.02 seconds, it says, where am I inside the call stack? Which function am I spending time in right now? And it records that information. This is in contrast to Python, which is explicitly timing every single call when you do cprofile inside Python. So two different strategies for profiling. They both work. Let's run it. Okay, now our prompt has not returned. It's running because it's slow right now. I'm using this small set because I don't want to go over the entire data set that took, I don't know, what's the longest it took people? People were talking about an hour, 2 hours to do the bootstrapping across the entire data set. We've got the contingency table inside here. That's what I was loading up. But how long did it, yeah, 5 or 6 hours? So that's why I'm not doing it. I'm not profiling it for 5 or 6 hours. I'm just doing it for a short time, however long it's taking here, this T1. So what I'm doing inside here is my contingency table, just a few elements. I'm seeing how long it takes to bootstrap these and get the result out for those. So this only takes 12 seconds instead of 4 hours, so we can see some results. Okay. So I ran that, I turned the profiler off. I look over here. Now I have this file rprof.out. I could have had the profiler write any file I wanted. This is just the default. I can pass it an argument and save many different profiling things, but I'm just using the default. So it writes this file. We can look at it. rprof.out. ASCII text with very long lines. We can process it using all our favorite shell tools if you want to be a glutton for punishment. So it shows you what it's doing at every interval. So we don't need to get into the format because R has a built-in function for summarizing it. So let's just look at that. R summary rprof. So if I don't pass it any arguments, I just get this, it just looks for that rprof.out file inside my current working directory. And it finds it and it spits out a summary that tells me what's going on. So this is the summary that we're looking at. System.time. So these are the total percentages where our program is spending its time. When it says 100%, that means of the time we were profiling it, every time it looked in there, it was in a call to system.time, which makes sense because we were timing our whole lapply loop. By that same logic, we had an lapply with an anonymous function inside the lapply loop, and that's what these lapply and fun are. Then it was spending a ton of time, well actually, the same amount of time in all of these, right? lapply, replicate, sapply, bootstrap. So bootstrap is the only one that we wrote out of these. And then it's spending close to 83% of the time inside KLD, which means our KLD function is slow. Okay? Somehow this really idiomatic, nice function that we wrote, it's very simple, it's got very little code, is slow. And then you're like scratching your head, like what? It's like a very simple, easy function. Why would that be the case? Why should it be slow? Any ideas what could be happening? So it's just one clue. All these things are clues to piecing together the performance thing, to identifying the bottleneck. And this is not easy, by the way. It takes a lot of time and experience to understand what's happening. We see all these ops.datatable and ops.dataframe are the next kind of biggest, which means it's spending a bunch of time in data frame operations somehow. So to see why that might be the case, so let's see what does the function actually do? It's our bootstrap function that we were calling here. So you could read through it and try and figure it out, or you could look in it while it runs and see what's actually happening. And the latter is a lot more efficient. The techniques are the same as debugging. So let's go in and see. Yeah.
Is there a way to get the actual stack?
Yep. But this is, I think, a little bit easier what I'm going to show you here. But you can look at things like stack frames.
Or the call stack in the profile?
The call stack in the profiler? Yeah, that's what's in the rprof.out is essentially the call stack.
Or can you visualize it? Rather than just looking at a list of items.
That would be really nice.
We use lots of other profiles sometimes.
Yeah, probably one of the newer ones does in R, or the ones for RStudio. I imagine they've got something. But I don't want to go too far down that. Let's play around with our Bootstrap and see what's going on. So the data I need to work with here is this digits count by list. Digits count by list. I was using the second element here. So this is the argument that's getting passed into each call to the Bootstrap. Let's run it. Bootstrap of this. I call debug once, and run it. Okay. Now I'm inside the actual call to Bootstrap. I'm inside this code as it runs. ls, I just entered. I have my element argument, the thing that it was passed. So the thing we want to know is what is this element? It's a data frame. Okay. So then we mess around with the element. But what I'm wondering here is inside the profiling, we were spending all these times doing things with data frames. And we have this little tiny data frame that we're using, dim of element. This is a 1x9 data frame. So data frames are really handy when you have a big data and a whole bunch of columns. But for this little thing, it looks like we're wasting a lot of time using the data frame methods when we could be using maybe a simpler data structure. So what's the simpler data structure we could have here? A vector, yeah. Just some basic plain old R vector. And then when we call these operations on these basic vectors, those should be fast. And then all the stuff from the data frame methods should kind of go away, disappear. So let's see if we can make that happen. So I guess I should write this out. This is our hypothesis. By using a vector, if each element were a vector, then KLD might be fast. We've not proven any of this. We just have a hint because that's where the profiler is spending its time in these data frame operations. So let's find out. And so I'm going to make some really minimal changes. Instead of this Q table being the actual distribution table, let's look at what this thing looks like. Actual distribution table. And what is this?
QX.
Hmm?
QX.
QX?
Yeah.
Oh yeah, right. Yeah, this is our Q table. Okay, so this is a data table which we got from FRead, probably. Inside R. So when we were looking at the profiling, we see a bunch of stuff for data frame, data.frame, and a bunch of stuff for data.table, I think. Let's see. Okay, so it's still spending time in the data.table methods, whatever those are being dispatched to. So let's make that into a numeric. So actual, and I don't want to write over it, actual distribution 2 equals that, as dot numeric, this thing. Convert it to numeric. Check that it looks like what I think it should look like.
I forgot the two.
Thanks.
No, wait.
This one, 2. Okay, good. It's a number, vector of length 9. Class. It's numeric. Okay? So we'll modify this KLD, KLD2, use the second version of that, run this. And here I need to convert something instead of the property table, I got to convert that thing into a numeric somehow. So let's just try the simple way of doing things. Equals P here, as dot numeric, prop, table, each sample. Made my changes. Run them all. And now I can I was changing KLD 2 because I was using this actual distribution table 2, the one that I converted into a numeric. That's why I was changing it.
Yeah, but you have bootstrap, this is the last line, is still LD, it's
Oh,
not LD2.
thanks. Thank you very much. Yeah, that's a mistake. Glad you're looking closely.
Oh, it happens a lot of time.
Yeah, these mistakes are totally easy to make. So KLD2 as numeric. Okay, that should be all good. Fingers crossed. Then run all our profiling here. So instead of Bootstrap, I'm doing Bootstrap 2. Instead of T1, I'm on T2. Okay, I think everything's changed. So many things change. Could not find function Bootstrap 2. Okay. Bootstrap 2. Okay, I forgot to name that thing Bootstrap 2. So original time, T1, I think. And then our next time is T2. Okay. Success, apparently. Hopefully.
Was that because of the warnings?
Huh?
The
Warnings! Oh no! Pay attention to warnings. Ignore warnings at your own peril. So I ran it and it gave me this message. There were 50 or more warnings. Okay, this is something to look into. Let's find out what the warnings are. If you don't remember, luckily it shows you how to do it. Use warnings to see the first 50. Okay, let's see what they are. So this is better. But there are warnings. Let's look at them. Warnings. Okay. Have people ever seen this? Longer object length is not a multiple of shorter object length. An element divided by Q table.
Elements of the table aren't the same length.
Yep, they're not the same length. Yeah?
Because there's missing digits, so there could be a non-count when you do it in there.
Yeah.
So
Okay.
that
Comes from missing digits. Oh, nice. You know the solution too. So we can convert it to a factor to fix it. To a factor to account for this. So let me demonstrate what I mean is the problem. So the problem that we're doing is something like this. 1 over 10 divided by 1 over 3. Okay? This is the warning that we got. It's equivalent to this. What this code does, what R does is recycle 1 over 3 to be the same length as 1 over 10. So an element, a vector of length 3 got recycled to be a vector of length 10. You almost never want this behavior. I mean, I've never even seen a case where it's correct. And here is one of those cases. So if you get this warning, you're pretty much probably, almost certainly wrong, doing something wrong. Has anyone ever meant to do this? No? Okay. Yeah, and this is one of those things where people are like, with R's design, like, why does this not raise an error? It's just a warning. So let's fix it.
Well, maybe it could be useful when you are trying to alternate the sequence with 1 zeros, 1 zeros.
Yeah, but then they should line up, right? Like they should be even factors. Like if I change from 1 over 3 to 1 over 2, then it lines up. But if they don't line up, yeah. Yeah. Almost always bad. Okay. All right, so the trick, Jared knows, is to make it into a factor. Use a factor. So we're looking at something like this. Table 1 through, just to show you, we're doing something like x equals sample 1 through 2. What is sample? Size equals 10, replace equals true. Table x. So this tells us how many times the 1 and 2 appear. But if there was a 3 that was possible that just only happened with very small probability, we could do something like y equals sample 1 to 3. What is the argument? Prob here? Yeah. Prob equals c. So 0.499, 0.499, And 3 is rare, so this would be 0.02. 02?
0.
02. Close this off. Okay, so we ended up only getting 1s and 2s. If you convert this to a factor here, let's see. Now we get the table that we want with the 0 counts as they're in there. So this is the trick for getting around this particular thing. Any questions on that?
Why would the factor work?
Why does the factor work? Because levels is stored as an attribute alongside an integer vector. Okay, so levels, we know all the different possible categories that it can take on. In this case, the different possible categories are 1, 2, and 3. We only happen to see 1 and 2, but we know that there's a third category that just doesn't appear. That's the meaning of it. Gary, you smiling? You did this like...
Yeah, that's sort of like, I did it sort of different, but pretty same idea.
Okay. Yeah. All right, so we're going to integrate this inside our code. Bootstrap 2 goes to Bootstrap 3. I think our KLD function doesn't need to change. This is still good enough. There's nothing where we can convert this into a factor in this place. Ugh. Okay, so let's go ahead and fix it while we're at it. So applying the same principle that I did here, this sequence of 1 to 9 is the thing that needs to be a factor for this to work. Fs as dot factor, sequence 1 to 9 right here. Bootstrap 3, I can still use KLD 2. I think that should work. It's T3 now. Bootstrap 2. Copying and pasting is perilous. So dangerous. Oh, no warnings. Sweet. Everything must work perfectly. T1, T2, and T3. Let's look at all these. Okay, so we keep, so the point of this is when we changed our code from what we originally wrote that we thought was clear, that's why we wrote it in the first place, we made a bug, we made a mistake, we introduced a bug by doing this. And now I remove the bug by doing this kind of trick. So this is why you shouldn't ahead of time try to optimize your code. Just write it in the way that you think is the most clear way. There's a famous quote, premature optimization is the root of all evil. What we're doing here is optimization. We're making our code faster. In that we're introducing bugs, we're changing things, but we fixed the bug, so that's all good. And we seem to have got an order of magnitude speed up from where we were at before. So we went from 12 seconds to 1.4 seconds. It may not seem super impressive because it's just 12 seconds, but then just put hours behind it, right? Because this is going to run across the whole data set and take forever. So parallelism, we could have maybe gotten some speed up to the number of cores that we're doing, but by refactoring our code, benchmarking it, profiling it, and changing it, we're also getting orders of magnitude speed up. When we combine all these techniques, then we get real speed up. And by the way, that's when you should use parallelism too. It's after you profile it and identify if you see it's all stuck in one big part, like, oh, maybe this part can be parallel. Not everything, just one part. So let's look at the profiling results to see what's happening. Again, everything is inside the system time and the bootstrap function. So what about table? Table takes 25% of the time in this case. Do you think there's a way to make table faster?
Convert to numeric vector?
From a factor?
No, to a vector.
Which one? Which should be converted to a numeric vector?
There's an element.
The elements. So we're replicating a factor here. So what we end up having is samples of big factors. So we're tabling a factor. So these are counting up categorical variables inside R. And by making this into a numeric, I don't think that will make it any faster. It's just my hunch.
No, I mean it's element.
Elements of what?
Or convert the element to a.
Oh, element in this case?
Yeah.
Oh yeah, what is that being called on? Bootstrap 3. Because we are spending a lot of time in this T, I think. Let me check. Yeah, so T is right up there, the data frame. So we're spending 23% of the program time inside this T for this element. So this could be numeric, right? In the same way, it's basically applying the same trick and getting it down faster and faster. So you can keep doing this ad nauseum, right? Keep doing it until your program is fast enough, is the rule. But I'm not going like the process is exactly the same. It's just another iteration of the same process, so I don't want to spend your time doing this. But what is important is this table that is taking a lot of time. This table, let's actually look at it inside R. So table, we got all this kind of stuff. Oh my goodness. Just goes on and on. Dot call. Dot C. Okay. All right. So eventually, this stuff will go into C code. What was that? Tabulate. Okay. Tabulate. All right. Here's what I mean, so table calls tabulate. If you keep looking at the code, you'll eventually get down to C code. The sooner it goes to C code, probably the less you will be able to optimize it. So in this, the ways that it goes to C code in R, you'll see a .c, a .call, a .external, or a .internal. Here's a .internal, tabulate. So this is something that statisticians do all the time, count things up. We have reason to make this as fast as it can possibly be in R. And so in R, this is probably well optimized and really fast C code, and it's really hard to improve on that, typically. Just my hunch. So you don't want to be trying to improve things like plus, minus, mean, min, exp, basic math functions. You won't do better than than is already there. And table is kind of one of those because we go right into the internal here. Okay. Yeah.
So would it be faster to call the actual tabulate function rather than using table? Like, does that extra bit of a wrapper? Because that's what I ended up doing in part, because you can specify the number of things in tabulate, so you don't necessarily have to convert it to a factor.
Oh, cool.
But I just wasn't sure, is that faster to remove some of that extra stuff? that surrounds tabulating the call page?
It could be, but let's check. So the way that we check is looking at the profile and seeing how much is spent inside the call to table and how much is spent inside the call to tabulate. Let me see if I'll find that out.
Oh, yeah, there's a tabulate.
You see it?
Yeah.
Let me see it. There it is. Oh yeah, yeah. So there might be a lot of speed up potentially by that because this is only spending like 1.5 seconds. So all that other stuff that table is doing is you could possibly go down to the lower level. Okay, so it's just a rabbit hole of being able to use all these techniques. That is, call lower level functions, call C code, that sort of thing. All right. What else did I want to show you about this? Oh, it's just like with the test-driven development. Every time you're making new versions, so I'm actually copying and pasting them and writing them out so you can see that they're different. But you might be editing the same code and changing it. This is where version control is extremely nice. Like you want to make a commit every time you make a change to your function with this kind of thing. And every time you're trying to optimize it further and further. That way you have snapshots of it, hopefully at working places, all along as you're developing. And you can use your test-driven development to write tests that define how it should behave and make sure that they pass every time you optimize it. Okay, so the message is, look for the thing that takes the most time, whack it, make it smaller, best you can. That's the idea. All right, so that's any questions on this? Yeah.
If we use the tabulate, so we can get rid of so many like error checkings in the data function. Would that actually be safer or quicker? If you have to do the error
Like almost always going to a lower level function makes your program less safe, less robust
yes.
at the expense of speed. You get speed, you give up safety, convenience, robustness. Usually, almost always you want safety, convenience, robustness until you don't. Until you really need speed. Then you go for something like that. Okay? Any other questions about this? So by profiling, we saw what the bottleneck is, we fixed it, we make it go faster. Let me show you so here's this, I was showing you this program in the beginning that creates this SQLite database. It's here on our course website, so people who want to use it for the final project, feel free to download it. You can download it to your local machines. It's 6 gigabytes. You can put it on the cluster. The cluster has SQLite installed. You can even write it to scratch. I won't be mad. Other people will use it. So this is the actual database. So you download this. It shows up inside your download thing, and here's kind of a nice way to get started with SQL. There's this GUI, this IDE, DB browser for SQLite, and this is what I'll talk about for the next class. I'll give you an introduction to SQL and show you these. I just want to show you so you can play around with it and use it for your projects if you need to. You don't have to use this GUI. There's a command line tool for SQLite. But this is kind of convenient. It shows us we got these 3 tables: agency, recipient, and transaction. Over here you can execute SQL. So this is what SQL looks like. Something like select star from transaction limit 10. And then you see the same kind of table that we have been processing. But it's also a little bit different than the CSV file, because the CSV file is a denormalized view, and I'll talk about what this means next time. This will be your teaser for learning about SQL. But this is actually normalized. Okay, we can head out a few minutes early. I'll see you Thursday.
Did you get PyTorch loaded on the server? Did you say it was dry?
Yeah, I think so. Was it not working?
Yeah, I tried it on Saturday.
I can.
It's not a big deal.
Okay. Yeah. Let me check real quick.